on from where you get this data, but we are talking of about 20% of the total greenhouse gases are generated by agriculture. So it is important to do something, and we, with our technologies, we can really do something, and I hope that I will show you some examples. By sure, I will not talk in details about, but I want to cite it, the loss of food, the waste of food, that is huge. In principle, we are producing enough food for everyone on planet. But at the end, because of the waste, because of the not good usage, we know that there are parts of the world in difficulties. So, and again, our technologies can help, but it's a part that I will not touch. I will touch more how we can contribute in optimizing resources. And I really love what, if I'm not wrong, was started by FAO, this name of smart, precision agriculture, that is climate smart agriculture. Because as I was telling you, it is important nowadays to really work on being, yes, smart, to do smart systems, but climate aware. Not just because, of course, it's important from the, let's say, societal point of view, but it is becoming a must in terms also of financial issues, because of climate, of the problem of climate, we are losing a huge amount of money. So we have, by sure, to increase productivity with our technology, we can. To enhance resilience with our technologies, we can. To reduce the emissions, because we can optimize the use of resources, we can optimize and reduce the generation of greenhouse gases. But all these really important and fundamental targets must be put in parallel to sustainability in economy. So must be financially sustainable. So our huge challenge is to put these two things in place. So to do from one side something that is climate sustainable in terms of climate, and sustainable in terms of financial issues. So what is, and I guess you know what we are talking about, just a quick overview. We are talking of systems that are getting information from the crops, that are controlling the irrigation, and the information can arrive from sensors, from weather stations, also taken by drones running around the crop. Here is not indicated, but also satellites. And all this information have to be sent to a decision support, and I will go in details of some possibilities of how to send the data out. From the other side, from this decision support, we can apply intelligent algorithm for extracting the information that are needed by the end users. Talking about sensors, I want to highlight you one of the things of which I was, of course, glad, because I'm working on this from many years, and surprised that the World Economic Forums few months ago said that the wearable plant sensors are one of the 5 technologies about to change the future. So it is, and it is exactly what we are talking about today. So to let the plants do the talking. So I'm arriving from biomedical engineering. I work a lot in biomedical engineering, and now I moved the part of my group working on from wearable for humans to wearable for plants and soil. And it is exactly one of the topics, main topics we will talk today about. So, which is the structure that I see that is needed for setting up our system? We have to put, it's clear now, to put sensors distributed on the plants, so leaves, twigs, roots, branches, and also in the soil, because the agronomist trained me about the fact that soil and plant are a unique system. You cannot split them. And so having this information, we can see the health status of plant and soil. We can optimize resources. We can optimize the use of pesticides or reduce it. But we have to spread this information, to send this information and do what can be named the plant area network or an internet of plants, because we have to transmit this information in a place where probably we have 0G connection. So this is one of the issues. And from the other side, we have to send everything to the cloud, where in the cloud we can do also more advanced processing of data to give the information to the farmers. But we know edge computing, so in agriculture is fundamental to edge computing, so in place, inside the crop, sending out when needed information to the cloud to be processed at a higher level. So there is a lot of work to be done. So which are the main goals? The main goals, by sure, is to do a sustainable precision agriculture. As I told you, sustainable in terms of climate and sustainable in terms of financial issues. And we have to do it, our challenge, to do it for optimizing nutrients, resources, improve, for example, the first important resource is water, so irrigation systems, but not only to reduce chemical treatments, pesticides, and the first attempt that we have is to produce alarms and warnings for the decision makers. By sure here, AI can be a point, and I will share with you at the end of my presentation my view about the use of AI in agriculture. And don't forget also the fact that we can also introduce automatization inside agriculture. So I will show you an automated system for irrigation. And we have to be less invasive as possible, because we have in front of us living elements. So we have to detect the health of the plant, the watering status, transfer the information, give information to the farmers, and give real time in terms of plants. Real time doesn't mean nanoseconds or microseconds. For plants, real time means hours, days. So, but something that is related to application. By sure, the final goal is to improve food safety and quality. But so, which is the strategy we need to apply to feed the roots? So, to put in place something that can answer to the requests that I just listed before. As I told you, I want to go inside. And so I want to give sensors, to put sensors in the plants, in the crop, in the pipes, in the soil, and all these systems has to be interconnected, and the plants must talk together. And I took this idea from a book of Stefano Mancuso, who is an Italian biologist of plants, very expert also in agronomy, and he wrote that the plants already talk each other today, and I get some ideas. One is, yes, but if they can talk together, they are interconnected. And he wrote that they did experiments in which when one plant in a corner of a forest has a problem, after a while, the other plants in the forest, they raise up the countermeasures to the problem, even if they don't have it. So the first plant told to the others, there is this problem, be aware, start to protect you. So I want to apply the same, let's say, concept, okay? So to go inside. And also the other important concept is that I want to go in place because, I always do this comparison between biomedical engineering and medical doctors. When I have to get the information of a guy who is not healthy, usually I can look to this guy, maybe he's sweating, he's red, he's white, I see that he's not good, but I don't know which is the problem. I immediately use a temperature sensor. I immediately put some electrodes in case for getting the ECG. So I go inside the system for getting, let me say, in an electrical way, call it system, no? And to get the information. So here I say Satellites, videos are very important and must be used, but they are not enough. So it's needed to change a little bit also the paradigm. And by sure how we have to do it. We have to do it doing application driven. So we as engineers, we must be very humble and listen the farmers. The farmers must tell us which are the needed data, which are the needed feedbacks and the necessary countermeasures we have to put in place. So we have to work with farmers, agronomists, biologists of plants for understanding which are the real needs and don't invent us the problems, but ask them which are the problems. What we have to do? By sure, multidisciplinary efforts, because I mentioned many different fields of science. So to have the possibility to set up the right sensors, and in this point, we have the key of why up to now, in fact, people are asking me, but you were working in biomedical engineering for a while. Why in agriculture we don't have the sophisticated solutions that we already have in medicine? And I said, because we were not ready. Our technologies up to a few years ago were not flexible, were not transparent. In a plant, you must be flexible, you must be transparent on a leaf. If you put something not transparent, the leaf dies. So, and in particular, powering. We cannot think to put in a field batteries. So we have to think about energy harvesting. And only recently we have quite good efficient energy harvester. We have good low power electronics. So now, in the recent years, we can start thinking to have available technologies for agriculture. Even if you can think that agriculture is a simpler domain, is not at all, because the challenges that we have as technologies are very tough. And by sure, we have to insert to use smart electronics, AI, and also to do this in-plant communication. And I did not list, but I did not say it up to now, but it's important also to conceive user-friendly interfaces. We have customers that are not experts. We cannot expect that they are experts. So this is a challenge also. But the two challenges that we have in front of us are that in respect to biomedical engineering, where you can have, by sure you must have low power, wearables, implantable system, they must be low power. But in a biomedical engineering, for a pacemaker, everyone is ready to pay what is needed for saving his life or her life. In agriculture, uh, you cannot think to spend too much money for an apple tree. So the huge challenge we have in front of us, and on the other side, as scientists, is a fantastic thing, is that we must set up in parallel ultra low power and ultra low cost devices. Else, maybe they can work perfectly, low power, but nobody will buy them because they are too. And it is the situation nowadays with plenty of sensors that are not so much used because they cost too much for the application in agriculture. So low power and low cost. So if I was clear, let's see what we can do as collecting the our ideas and our competencies for reaching some solutions. I start from the basic thing, data. Guys, I always say to my students, do not do the gigo memory. I don't know if you already listened to the gigo memory. You saw you have a LIFO, last in, first out, the FIFO, first in, first out. The gigo is garbage in, garbage out. If you put in a system garbage, you will obtain garbage. So the production of data is fundamental. You can have the most complex AI system, but if this AI system is probably very good, it receives bad data, it will give you bad results. So the production of data, and so the setup of good sensors, efficient sensors, robust sensors must be done. And the challenge, low cost, low power together, it is a challenge and it is something in which is also good to work on. Nowadays, business as usual are visual, as I said. So solutions for getting by cameras, by satellites, information. And also some electrochemical sensors are up and running already. In terms of okay, images, I don't go in details because you know very well, you can get images looking at some problems I have on my leaves. With satellites, I can see the status of my soil, not only by RGB, but near infrared, multispectral analysis systems are needed. For example, here I can use images and machine learning for predicting which will be the production, to understand if everything is running well, and also what is very important nowadays, and it is one of the tough challenges we have, it is to detect these volatile organic compounds. Volatile organic compounds is one of the way how the plants talk, because they emit ethylene, methyl jasmonate when they have a problem, when they have an issue, probably depending on the gas specific. They say also, as I told you, that the plant talk each other. They say that they are using fungi in the soil, probably. I'm not an expert, but what I was reading from the other side, but also by volatile organic compounds. These volatile organic compounds can be measured by electrochemical or chemofluorescent, and we know that electrochemical sensors are unstable, not selective, not so robust. So that here, and I know a lot of groups around the world are working because now the market is becoming interesting for studying low cost electrochemical systems for measuring what I will show you soon, but some of the volatile organic compounds that are emitted like ethylene and methyl jasmonate. And here, guys, I'm just showing you some examples. There are plenty of them. But these sensors must be efficient and low cost, and this is not trivial to do it. Also because talking about the soil, so the nutrients that are mostly nitrogen, phosphorus, and potassium are measured by, again, conductivity, electrochemical, and there are, I show you here an image of a already commercial sensor, but they are too expensive because Brazil, US are some examples quite specific in respect to the rest of the world, because you and US, you have very large factories. In, uh, in, in average, in the world, the 80% of farmers, they have farms with an extension of crops lower than 2 hectares. So you can imagine for the majority of farmers, the technologies nowadays available are too expensive. So the spread of the technologies is not possible because of it. Last but not least, is also interesting to measure the evapotranspiration of the leaves, because it's how the leaves, how the plants, they breathe. And also here we have very interesting methodologies, very interesting sensors already, but again, too expensive. So for generating data, we have really, guys, really an open field in front of us of a lot of work and a lot, of course, of possibilities to have and possible, setup of new companies, new ideas, startups for having very good results. Okay, by sure, this is again business as usual. In this case, environmental sensors are already up and running with also decent prices. So for measuring which are the parameters of the environment, light, humidity, and also in the soil, some interesting sensor for measuring and in this case, work has to be done because the nowadays sensors I will show you later are quite too much expensive. So, but for soil moisture and, for example, the presence of fertilizers. In Torino, but not only in Torino, we started this trend a few years ago. people started, and I had this idea with a colleague, Yossi Shaham, you see here as co-author of this paper. We said, okay, but we can measure impedance, bioimpedance of plants, because in humans it's very useful bioimpedance. It can give you a lot of information. If we try to measure impedance in plants, it is a very simple circuit, no cost, low cost, so perfect for our purposes. So we started working on tobacco plants, and tobacco plants are a perfect model for electrical engineers because they are a model for almost all the standard plants for fruits, for corn, all these type of fruits, because they have two channels, the phloem and xylem, that are two channels in which the products from the soil, so minerals, are going up, and the product for the chlorophyll and photosynthesis, so in general sugars, are brought down. So, you know, these channels, they have charges, they have possibility to have electrons, so we can measure an impedance. And so we started putting our electrodes in the plants. And you see here, I show you what happened. It happened that this is the first row is the soil water potential. That is the standard measurements nowadays done. So we did this measurement for, of course, calibrating and validating our measurements, where you see when the soil is becoming drier here, the negative, it goes negative. And when you water your plant, it goes to zero. Zero means that the soil is watered, is humid enough. And after, when it becomes drier, of course, it goes down. The impedance has an opposite because, you know, as soon as I have more minerals, more ions, more charges inside my channels, of course, my impedance is lower because I have a better conductivity. As soon as my soil becomes drier, of course, I miss charges, I miss electrons, and so my conductivity decreases, and so my impedance increases. And you see it here. As soon as I water my plant, you see I have a decrease in impedance. And guys, look at this, real time. We are talking of days, okay? Days in change. So it's not so quick, but it goes down and it is very evident. And after it restarts to grow up, to go up. Uh, Here you have the average of the modulus, but you see here, and I will show you later, what is this periodical behavior with raw data that I have in my impedance modulus. The phase has similar information, but to measure the phase is more complex. So we will not use the phase. We start thinking to reduce complexity, to reduce the cost of our solution. So, by sure now I guess it is clear that, of course, impedance gives you a lot of information, and we will see which informations. From the other side, we have also the need of other sensors. And so we need to do sensor data fusion for extracting information. One of the most important efforts that groups like mine are doing around the world is to nowadays use as many as possible sensors for measuring everything, but the target is to reduce them to the also evident the increase of impedance when I watered. You see here the moisture, and you see here we are measuring temperature, air humidity, ambient light, and we are also measuring in parallel other measurements. And putting all this together, you can have the information. Now I'm going to zoom, but remember that um, each label here, it is, you see here is 1 day, because zooming inside the results, you see this behavior, okay, with a periodical change, and we will see it later what is, but I have an increase in impedance and decrease in impedance. So we know that here the plant is entering to suffer. So it is having what is named the water stress. So you can decide with impedance when it's time to water it. You water it, and after the plant becomes happy because it is in a situation which is in equilibrium with the soil and can get the nutrients. And what is this periodical? This periodical sign, a signal, it is what I call the electrocardiogram of the plant. Here are days. You see that, okay, the beat of a plant is daily. It is the circadian cycle of your plant, because you see when your plant is going to sleep and when your plant is it wakes up and it starts working. Because when it starts working, your impedance goes down. As soon as the plant starts having activity, it goes up. Here is not a mistake. Well, I did it for mixing two things. Stem impedance in earth. Okay, I will reject one of my students doing this, but I explain you why. Because in the next slides, I will show you how I'm putting in relation the frequency in respect to the stem impedance. But don't mind too much about this. Mind about the fact that now measuring the impedance, I have a possibility to have, of course, I know that physically speaking is not the same thing, are two different, the plant doesn't have heart. But from the other side, the information I have from the signal is the same, because I see that my plant is living, the amplitude, the shape of the signal, it has a similar content of information as the ECG in a human, because it tells me how much is active, if there are problems inside my signal. So this is why I call it the ECG of the plant. So after that, I gave you this general introduction to the sensor, and in specifically the sensors we are working as innovation in my team. I am happy to show you two different examples. One, as you can imagine, it is to the node, we call it node, from where we measure, for example, the soil water potential, and we use LoRa communication. LoRa, it is becoming a sort of standard, because nowadays it is at the end one of the most efficient, because it is really long range, kilometers, in respect to a very low power consumption. Here you see now the electronics that you will see are of course not optimized, are not the final goal, but we did these electronics for starting, and the idea showing that by our idea it works. So impedance and frequency. Why I was mixing impedance and frequency? I was mixing it because for again optimizing cost, reducing complexity, we said, but with a relaxation oscillator, if we put in the loop in the feedback of a relaxation oscillator our plant, the impedance of the plant, you know, probably some of you or most of you studied the, uh, the relaxation oscillator, that is one operational amplifier with some resistors and a capacitor around, and it generates a square wave with a frequency, or a period, but a frequency proportional to the impedance in the loop, in the feedback of your amplifier. So if we put, instead of capacitor, we put our plant in the loop, we have a frequency proportional to the impedance of the plant. And I'm doing this with the simplest possible circuit, 1 op amp and few resistors. The cost is nothing. It is very simple. And from the other side, I can obtain the needed information because here I don't need to measure the absolute value. I never mention if even if I had it, the value of the impedance. I have to see the trend. I have to see the differential changes. So I don't need to be, and this is important, low cost, low power. But we are lucky that we can reach our goals having lower accuracy than in other systems. So the trade-off is to find not so accurate, not so precise systems, but enough accurate and enough precise for having the information you need. And in this case, this idea was exactly the solution. So, one example that confirmed me that we were on the right side, it is this strange plant. This strange plant had this behavior. You see here, impedance, now I guess that is clear, it increases, so the soil is dry. After it goes down. Goes down means you water it. No. This plant, the 28th of around December, was not last year, no, a few years ago. This is one of the first experiment. You see, measuring at 10 kilohertz of frequency, was not watered, but the impedance went down. Wow, why? And we did not have any clue because this plant was one of four plants inside our laboratory, equal to the others with green leaves. It did not show any problem, but it went. And after every part here, every section is 1 day. After some days, the impedance went up. So why this strange behavior? Not due to any reason. And visually speaking, it was equal to the other ones. What this plant did, after a few days, this plant died. So, guys, I knew with the impedance few days before that this plant had a problem. Uh, of course, me, I'm not expert, so I did not know why. And the biologists of plant that I interviewed, they told me, listen, Danilo, probably because also for them is completely new this idea. They told me probably the plant did what as humans we do when we are in trouble. We start opening all the possible channels for breathing because we have to recover energy. So the plant decrease the impedance, open all the possible channels for surviving. But you did not do anything. She was telling you, I'm dying, I need help. You did not listen, the signals, and so the plant died. And I tell you, this is one plant. But because when we started, we were perfect killers of plants because we are electrical engineers, so we were not so good in growing them. Now, my guys are very good. I tell you, this similar behavior, scientifically speaking, it is repeatable in all the plants that are dying. So now we are working for giving, of course, also biological explanation of what is happening, and we plan to exit soon with a paper on it. So we know the plants, the health of the plants with not only the impedance, but also with, for example, in this case, we put sensors also in the soil. And we said, okay, let's set up a project in which we control the status of our soil and plant. We transmit it to the central cloud. We have algorithms here. We use LoRaWAN again, and we control the pumps of irrigation automatically. So we decide when to irrigate when is needed. And this was done on 3 real crops, 2 of apples and 1 of kiwis, where sperimentale means our part of field where we have our automatic irrigation. Aziendale means irrigated business as usual by the farmers. And we did this in 3 different crops. We used very not so optimized electronics, but we did it to be sure that we were able to measure it with a lot of control signals. Okay, so don't consider the plan is to really to reach to a very small electronics, very low cost. But what we already started in this measurement board to optimize the consumption, so to set up ultra low power electronics. This battery, and again, I don't want to use battery in the future, but we had to prove that everything was working. This battery is in the field from more than 2 years. So we did we started proving that we are able to do ultra low power. And now, of course, we are working to do the second version, the further version of the system, avoiding batteries, optimizing also the cost and the dimension of the board. And then from the other side, of course, we set up electronics for controlling the pumps. In these electronics is not a big deal because usually, of course, you are in a small box, you are in a place where you have power because here you have to control the pumps. So in this case, you can use really standard electronics, is not a big deal. So what we did, we took the measurements and in cooperation with agronomists and experts in watering and irrigation, they studied this water retention curve, so studying the soil, of course, depending on the crop. And these colleagues from University of Torino, they gave us the thresholds to work with. During the season, you can also dynamically change because they change these thresholds. So we did this with them to optimize our system, deciding when you pass the threshold, you irrigate, when you count down to the threshold, you stop irrigating. And we obtain these results. This is the results of last seasons of one of the 3 crops, but all the 3 we had the similar results. And you see here that at the end of the season, we saved, we are the orange one, the maroon one here, almost half of the water. So we saved half of the water. What is very interesting here, it is also the month of September, because in September we irrigated very much more. So I was curious because again, I was starting saying we did some mistake. I asked to agronomists and they told me, no, you did the good job because September last year in Piedmont, my region where these crops it was very hot and no rain at all. Big farmers in September they harvest the apples. So after the harvesting, they stop irrigating also because in Piedmont, in half September, start of October, it starts raining. So there is no reason why to irrigate. You just wait the rain. Last year, we did not have rain up to November and it was very hot. So they told me the plants suffered. The plants, the not irrigated plants, they suffered, and probably this year, in fact, I'm waiting the results of this year, they will produce less. Your plants were happy, so you treat well your plants, so you did a good job. And even if we irrigated very much more in September, again, we saved half of the water. But you can tell me, yes, but you saved half of the water, but did your crop survive? And the good news are that we had the farmers weighted the 2 productions, and the weight was similar. Also, the diameter of the apples in this case, they were inside the requested range. They were 78 millimeters. And they told me your plants were sweeter because I used less water. So they were, in terms of quality, they were even better. Also in terms of lasting, because they are sweeter, so they can last more in respect to the others. So at the end, the farmers were very happy. And I tell you, the best results of my project was, okay, these are very good results, but it was that the project ended last October. I said to farmers, listen, I have everything mounted. For me to collect data is precious. I will leave everything mounted, but the project is finished. Do I have to unmount? They told me, no, no, leave it. For me, that part of the crop, I forgot it. You did a perfect job, leave it. And guys, this is a fantastic result that three farmers were happy. And I tell you, two of them were young people, so maybe more, ready for technology. One was a historical producer. Well, all of them were happy. And because one of the big issues, big challenges we have is to convince farmers, to convince the end users that our technologies can be useful. This is by sure, still they are very skeptic. And so these are fantastic possibilities, fantastic projects in which you can show them that you can be helpful. Well, just to move, I told you we have data. We have now how to use data with some real examples, how we exchange data. Locally, we proved in 2019, we proved that because the channels inside the plant may have charges, we can use the plant as communication medium. So we transmitted inside the plant 50 kilobits per second. So we use the plant as a wire. So the idea is you don't need to go to do complex things. Just put your sensor, transmit the data inside the plant, and maybe on the bottom of the plant, you can put a box with maybe a large solar cell and there to transmit. And also I said, okay, but if I can do it inside the plant and the plants are talking each other, if I put two plants close a signal, do they communicate each other? And we did these experiments. This experiment where we put in these plants our relaxation oscillator generating the frequency and we inserted this frequency inside the plant. So, guys, in this frequency, now I hope that is clear, you have the impedance of this plant, you know how much this plant is healthy, so it's a good information. And we transmit it through a plant, through the soil, and we put from the other side a receiver. And this is what we received. And we received, by sure, a signal with a frequency proportional to the frequency of the transmitter. So the second plant is reading the health status of the first. And also, guys, the amplitude of this signal is proportional to the impedance of the path, because as soon as this impedance is lower or larger, you have a lower or larger um, reduction of attenuation of your signal. So you can have really interesting information. And these are the signals. In this case, I show you directly the frequency, so inversely proportional to the impedance. So you have here the frequency decreases when the soil is drying, you water the plant and the frequency goes up. And you see here from the soil water potential, the comparison, the validation is perfect. But this signal is the signal related to the plant one, but it is what I'm reading in plant two. So they talk each other. Good. Last, AI in agriculture. I mentioned we need AI, intelligence. So, but as I hope that I was clear, the first thing that you need human intelligence. Human intelligence for generating good, robust data. Second, to train, to set up your network, your artificial intelligence, your machine learning system in the right way, useful for agriculture. After, the AI can be very useful. Of course, I mentioned about crop and soil monitoring, but also nowadays is already using for controlling the robots inside the crop and also for doing, I mentioned, predictive analytics. So it is a very good tool, but guys, please, now is a trend. Everyone wants to use artificial intelligence, but be careful to use it well. This is just the key point. Well, in the meantime, because I'm okay doing a CAS Society distinguished lecture, I'm happy to share with you before finishing the initiatives. If you are interested to join us and to work with us in agri-food electronics, and this is transactions that I founded a few years ago. It started last year, and it is the first journal in IEEE about agri-food electronics. So, of course, if you have good research works, please consider to submit them to TAFE, the transactions on agri-food electronics, where you can submit. Of course, I was just talking about plants, but you can talk of livestock, food, but this is agri-food, so also production, safety, processing of food, food transportation. So, of course, it has a larger view. And connected to the journal, there is the conference that was this year in Xanthi in Greece, the CAFE, Conference on Agri-Food Electronics, and the next year will be not so far from you, because it will be in Montevideo from October 1st to the 3rd. And so, if you have ideas and works on it, please come to join us. And for joining us, if you are interested, even if you are students, it is good maybe jump us. The past chair is Victor Greenblatt for Synopsis Chile. In this case, me, I'm the chair. The vice chair is François Rivet from Bordeaux, and Matthias Miguez from Uruguay. It is the one who will be general chair of next year conference CAFE. So you jump me an email, and we are more than happy to insert you in this special interest group, where, as you can imagine, we exchange ideas. We send, for example, news about the conference, news about new special issues inside journals, and so on. So I finish. I thank, of course, first my team. This is my team, and my team is nowadays 60% still in biomedical engineering. The 40% of them are now working on agriculture. So, of course, I thank them because they are really the ones who are doing all what I just presented. And I thank you for your attention, and I'm here for listening your questions. Thank you so much.
Thank you, Danilo. This was really, really interesting. When you talked about communications intra-plant, within plant, I was thinking the Internet of Plants.
Yes, exactly. It is a reality. It's not just rocket science.
Yeah, about 50 kilobits per second. It was. Yeah. To me, it was really insightful. I think it resonates a lot with Brazil, as you make some points. So I have many colleagues in the faculty working on sensors in bioengineering and also using optical technologies for sensors, and I can't see them trying to work them out, because these folks, the sensor is a sensor, right? And they apply to different domains of expertise. And in Brazil, agriculture is number one. So,
yeah, of course.
We should. I would be happy if there is some community that adheres to these initiatives that you are leading, TAFE and CAFE.
And it will be also a great opportunity, maybe, to do shared projects together. Maybe Brazil, with great pleasure.
Yeah. So I will try to do my best in disseminating in getting folks aware about this, because to me it makes sense. There is sustainability, there is efficiency, there are values, societal values, key values behind this work, and I'm a fan of this. Also, I'm a fan of this multidisciplinary stuff. I really I have not so many experiences in this cross domain. Like, you need to put together real people, real farmers, and experts in agriculture, and to me, this looks like, well, I talk to machines, not to people. This may be this one of the main challenges of this domain?
It is one, of course. It is like what happened in biomedical engineering a few years ago. It was the same issue that we engineers, we had to understand each other with medical doctors. Now, I guess the process is almost done. For farmers, it is just a start.
Yeah, biomedical. Yeah, this is one of the departments in our faculty which is very strong, and of course, I can imagine that they could also start some threads in this interesting domain. So, as I told you, I have plenty of questions here of the students. I will share them with you. They have done a great homework. This
good.
I'm very happy.
Bravi.
Many of them asking about the main challenges, and okay, you have touched on this. One that I thought it was interesting is, so far you are looking so you're looking into the domain of the sensor domain standalone, but I guess that connecting it to other data like radars or satellite images or other, so putting more sources of data information into this would be like a natural next step, or maybe there is something already going on. Can you comment?
By sure. Well, now it is one of the problems that all these systems are not interconnected. But the question, the idea, it is absolutely the key. So the future is to put all this information together, and artificial intelligence can help us, because by sure can help us, because I always say, you have in agriculture, I told you, real time means one measurement each hour. So you say, I don't need big data. No, you need big data. Why? First, you have more sensors, but you want to reduce the number of sensors, maybe there are not so many. But from the other side, to understand something from a crop, you need seasons of data. You don't just measure 1 month, you don't understand anything. So to understand and get good decisions, by sure, you can start, in 2 years, okay, the results of this crop, of half of the water, we did measurement for 2 years, okay? So measurement for 2 years are big data. So you have a huge amount of data, not in the short time like we have in other applications. You have few data each hour, but you need data for seasons. And so then you understand. So in fact, also it is one of the painful thing when you're working in agriculture, that you have results not in 1 month. So you can publish your paper maybe after 2 years of work, because it's natural. You cannot escape from it. By sure, now you can have, okay, let's say good results in the middle, but to have the best results or optimal results, you need time, and you need a huge amount of data. Even if you reduce the sensor, and it is correct, now the work is exactly satellite, environment, plant, soil, which are the key data that I need. And probably you need different data depending on the application. If you want to control irrigation, you need something. If you need to control maybe the pests that is affecting your crop, maybe you need other sensors. So in terms of commercial products, it doesn't exist the unique product that can do everything. Probably in principle it exists. You put all the possible sensors and it works, but it is not financially sustainable. So there are plenty of new startups already, because each startup can focus on a specific sensor, specific domain, and solving this problem.
Yeah, I was going to ask whether there were a large difference in the types of plants, like apples to grapes to others. Probably the same sensor that works on one, or the signals are not cannot be transported or generalized to another. I don't know.
It is generalizable, but as electronic guys, we know to do it. I mean, for example, as you talk about the impedance where we measure the frequency, the impedance of the plant, and again, the comparison with biomedical engineering is perfect. Every human is different. Every plant is different. Every crop. So you have humans, almost we are all the same. Plants are very different one each other. So you have differences inside the same plant, inside the different types of plants. But impedance, you just have to trim your oscillator to get the impedance. So the impedance sometimes is 10 kilohms, sometimes is 100 kilohms, sometimes is 1 megohm. So we know, and this is what electronics can be fantastic, because electronics are flexible. We can program also remotely now. So we can have very flexible devices. In this case, yes, having one solution fitting all. Of course, it's fitting for that application, but you can trim, you can, of course, the first thing that you have to do, in fact, we are doing now measurement in apples, kiwis, tomatoes, corn, we have, I don't remember, tobacco, of course. Every time you have to do just once calibration. You calibrate, and after that's it. And in fact, now, because we were out of doing everything, unsoldering and soldering new resistors, now we are putting programmable resistors. So
I like that message, because we work on programmable networks in software defined, so you can call your software defined smart agriculture.
Exactly. Thank you. It's a great definition. Absolutely.
Yeah. Software. So let's work out this concept, software defined. And I also loved. I was going to touch on this, the long time that it takes every experiment. Some of our students complain that, oh, it took me hours or the full weekend to run the simulation. And then I will tell them, look, there are other domains that takes 2 years. And imagine you have a bug in your system, in your sensor, and you need to redo everything. Danilo, this was great. I'm sorry we ran out of time. I should make it longer, this conversation.
Sorry, Mia was a little bit long. Sorry for it, but
we had also for glitch in the beginning. There's the first minute or so that the streaming. I will see how to fix it, but the main contents were recorded and streamed. I will share it again with you, and also the data as promised. Thank you so much.
You're welcome, and maybe share my email with your students. It was in my last slide. I'm more than happy to answer you and to enter in contact with you all.
Yeah, with my faculty colleagues in
bio. By the way, last 1 minute. I just set up from last year a new master degree in Politecnico. That is a master degree, as you can imagine, in agri-tech engineering. So if you want to come to maybe do some work, some thesis, we can do, and also an exchange of students with you could be fantastic. So just think about it.
Sounds excellent. Thank you so much. Keep in touch. And guys, students, see you next week. Last seminar of the season. Thank you. Take care.
Have a good study. Adios. Bye-bye.